Welcome back. Let's continue our advanced pharmacology lecture with everyone's favorite subject, MedMath. An important precursor note here to medication math or MedMath. There are numerous ways to get to the right answer. I don't propose that this is the only solution for MedMath, but what I provide you in this lecture is one way of doing MedMath to ensure that you get the right answer. And if you don't have an already established comfort with mathematics, I would encourage you to follow this method so that we can help you and coach you along the way and provide relevant examples that use this method to help you learn this process. Math is a subject that most people, dare I say all, have some level of discomfort with. The intention of you being comfortable with mathematics and MedMath is going to be critical to your functioning as a paramedic in the field or even an advanced EMT, as you're going to have to calculate medication doses to administer to your patient. Even if you're using a calculator, if you have no concept of what the average dose should be or be able to get a close guess within your head to check your own MedMath, you run the risk of giving patients erroneous doses and medication errors that can ultimately be lethal. So let's break into MedMath. We'll start slow and we'll follow this lecture up with a few practice questions that we can do together. I'll try and perform some examples as we go along today as well. Let's start with some terms. Mathematics review. Fractions are going to represent a portion of a whole number. So for example, the fraction 1 over 4 represents 1/4 of 1. It can also be expressed in a decimal form as 0.25. Decimals distinguish numbers that are greater than 0 from numbers that are smaller than 0. Dividing or multiplying by 10, when you divide, you're going to move the decimal place to the left. And I'll explain this with a drawing on the screen. If we start with the number 100 and we divide 100 by 10, we're going to move the decimal place 1 to the left. And so 100 divided by 10 would be 10. When multiplying 100 times 10, you're going to move the decimal place 1 place to the right, making it 1,000. So when dividing by 10, you're going to move the decimal place to the left. When multiplying by 10, you're going to move the decimal place to the right. Another important term to know in mathematics is that percentages, much like fractions or decimals, are expressed as part of 100. The definition percent means per 100. So for example, if we talk about 75%, another way of expressing 75% as a fraction would be 75 of 100 parts. 75 per cent, cent meaning 100. We could also express that in decimal terms as 0.75. 75% is 75 parts to 100, 75 over 100, or 0.75. Percent means per 100. This becomes important when we talk about medication calculations, particularly dealing with percent concentrations. Is there a medication you can think of that the dose or the volume of medication is calculated in percent? How about D50? Dextrose, 50%. It is 50% of weight by volume, or by mass rather, sugar to water. It's 50 grams of sugar to 100 grams of water. Dextrose 50%. Using that same logic, we can see that dextrose 10%, or D10, is 10 grams of sugar to 100 grams of water. One question you may be asking is, well, how do I know what 100 grams of water is? The standard unit of gram is the weight of 1 milliliter of water. So 1 gram of water is the same as 1 milliliter of water. In MedMath, we're going to use the metric system. They're base multiples of 10, and we use measurements of length and volume and weight, or mass. Our measurement for length is meter, our measurement for volume is liter, and our measurement for weight or mass is gram. And depending on where we move the decimal place will determine the prefix that we use to describe each of these. For example, millimeter or milligram, milliliter, microgram. I'll pause here a moment on this screen so you can look at some of the prefixes, and you're going to need to commit these to memory. Let's go over a few of them that will be important for what we do. The abbreviation ml, or milliliter. This is 1/1000th of a liter, or 0.001 liters. Milligram is 0.001 grams. Micrograms is 0.00001 grams. You can see the decimal expression here. You're going to need to commit to memory the ratios of liter to milliliter, grams, micrograms, and kilograms. A kilogram is 1,000 grams. Drugs are packaged in a variety of weights and volumes, and you need to be able to work interchangeably between these because your ordered dose may not be in the same dose that your medication is packaged in. This is particularly true when we talk about dealing with pediatric patients. Pediatric patients are stressful enough. We don't see a ton of pediatric patients in the pre-hospital setting. The last thing that you want to do is be uncomfortable, further made uncomfortable, by not being familiar with your conversion rates between milligrams and micrograms, or grams and milligrams, kilograms and grams, and having to deal with a stressful patient or a sick pediatric patient. So you're going to want to commit these to memory. Another truth of mathematics: you're not going to stay good at math unless you do math. If you're inherently uncomfortable with mathematics and converting things, you really should be practicing this every day, not just while you're in school, but you should be practicing this every day when you're out of school. Start your shift by just doing a couple very basic calculations. You can do this as you do your medication checkoff on your truck. Grab a medication, look up the pediatric dose for the drug, and create an imaginary patient that you would give that medication to. Let's say your dose is 1 milligram per kilogram. And say, okay, well, I've got a 25-pound child that I need to give this medication to, and just run through that math. And if you'll do that every day, you'll build the skill set and the repetition so that this then becomes intuitive and you're not having to manually do this out all the time. More mathematical principles. So let's talk about getting from milliliters to liters. If we're going from milliliters to liters, we're going from a smaller notation to a larger notation. So we would divide the smaller volume by 1,000. So for example, if we had a container here that had 1,000 individual milliliters, I'm not going to draw 1,000 dots on the screen, but you get the point. And we wanted to express that in liters, it would just be 1 liter. Because 1 liter equals 1,000 milliliters. We're only changing the focus by which we're grouping these things together. Milliliters is a smaller grouping, liters is a larger grouping. If we wanted to conversely go the other direction to express how many milliliters were in 1 liter, we'll call this 1 liter, then we would look at it on a smaller scale. And 1 liter is equivalent to 1,000 milliliters. Okay? Likewise, if we're going into weight conversions or mass conversions, a large unit to small unit, we would multiply the large unit by 1,000. So if we were going from 1 kilogram to 1 gram, we would multiply that 1 by 1,000. There are 1,000 grams in 1 kilogram. If we were going from grams to milligrams, we would then multiply by 1,000 again. If we were doing small unit to large, so grams to kilograms, we would divide that number by 1,000. All right, let's talk about some of the mathematical principles that we're going to use specifically for medication administration. The first is going to be converting pounds to kilograms. Using the metric system, all of our dosing will be based in grams and kilograms. In the US, specifically, we use pounds. So we need to be able to convert US pounds into kilograms. You'll need to commit this formula to memory, but I will give you 2 methods to actually perform the calculations. Kilograms equals the number of pounds divided by 2.2. So for example, if we were to take a 220-pound adult and divide that by 2.2, that patient would weigh 100 kilograms. We can use a shorthand method for this as well. So to calculate this same number within a margin of error, we can take the weight in pounds and divide it by 2 and then subtract 10% or subtract it by moving that decimal 1 place over. So we can do the same thing. Let's take a 220-pound person and divide that by 2. Half of 220 is 110. And then we're going to subtract 10% or subtract 11 from that number. And that gives us 99 kilograms. As mentioned, this works shorthand to be able to give you a rough idea if your calculations are accurate. Okay? 99 kilograms to 100 kilograms. I would encourage you to stop here and practice some weight conversions. All right, let's look at the medication calculation formula. The medication calculation formula in its entirety is this formula here. It's desired dose divided by the concentration of the medication, multiplied by the weight in kilograms, multiplied by the drops per milliliter. This is derived from the drip set, and so we'll talk about when you're going to use this. For most cases in EMS, when we're giving a medication infusion, we're using a 60 drop set. So that term in the end, if you're giving an infusion to a patient, would typically be used, the term that you would typically use to multiply would be 60 drops per milliliter. GTTS is the abbreviation for drops. You're not going to use all pieces of this formula for every medication calculation, though. It is derived based on what your order is requesting. So, for example, a bolus medication. A bolus medication, or an example of a bolus medication, is administer 4 grams of this medication or 4 milligrams of this medication. That's a bolus. You would only need to use desired dose over concentration. So let's say that you're going to administer 4 milligrams of a medication. That's your desired dose, 4 milligrams. Your concentration would then be how many milligrams in how many milliliters are you provided. So let's say I hand you a vial with 10 milligrams in 10 milliliters. That would be your concentration. You would plug that information in and do the math. We can look at it here. So let's say that your desired dose is 4 milligrams and your concentration is 10 milligrams in 10 milliliters. You've now set up your equation and you're going to perform your math functions. I generally coach students that the first thing that you should do is make sure that all of your terms match. In this case, we're looking at milligrams should match the denominator milligrams, and those match. The second step would be to solve for a single unit of volume. And by solving for a single unit of volume, I mean divide this term here by the number of milliliters that you have. So in this case, we would take 10 milligrams and divide it by 10 milliliters, which would give us a reduced concentration of, what's 10 divided by 10? 1 milligram per milliliter. So we can further simplify this calculation as 4 milligrams is our desired dose with a concentration of 1 milligram per milliliter. At this point, everything matches. We've solved for a single unit of volume. The next step would be to cancel like terms that we can cancel. And for that, we take our paired terms and we just cross them out. Our milligrams divided by milligrams is 1, so we can forget that. That leaves us with 4 divided by 1 milliliter. Now, for those of you that are more comfortable with math, this next step may make you uncomfortable, but I assure you that the algebra works out. The next step is to take your remaining term and move it to the outside. So we're going to move it over here because our bolus medication, we're actually going to give an amount of milliliters. And here's what I mean by that. Our desired dose was 4 milligrams, but we cannot go to the syringe and the vial and draw up milligrams. Syringes are denominated in volume, in milliliters. So when we go to actually give this medication, we're going to be drawing up a certain amount of milliliters that contains our desired dose of 4 milligrams. When we move our term to the outside, we're left with an equation of 4 over 1. That's 4 divided by 1, and that equals 4 milliliters. So you've gotten a couple of answers here to this question or this problem. First of all, you've determined the dose that you're going to give the patient, and it was your desired dose, and it was given to you as 4 milligrams. When you chart this information in your EPCR, you're going to document that you administered 4 milligrams of this medication to a patient. But you've also calculated the practical volume that you need to draw from the syringe to be able to give that patient 4 milligrams. That volume that you've administered is 4 milliliters. You've delivered 4 milliliters of solution containing 4 milligrams of medication. I would encourage you to pause here and go through some practice questions based on your guidelines, your protocols, and your medications at your local service. Let's look at weight-based dose or a weight-based bolus. Weight-based bolus medications take the previous calculation that we did with desired dose over concentration, and we then multiply that by a weight. Let's look at one of these together. Let's say that we're required to give a 1 milligram per kilogram bolus to a patient weighing 25 kilograms. We would set up our formula just as we did before. Our desired dose is 1 milligram per kilogram and our concentration, let's say the medication is 1 milligram per milliliter. And the weight that we gave for our patient was 25 kilograms times 25 kgs. And I'm not going to have room on the screen to write the kilograms, and I apologize. The first step would be to make sure that our terms match. Do milligrams match milligrams? Do kilograms match kilograms? And your kilograms are here on the 25. So those indeed match. Step 2 would be to solve for a single unit of volume. In this case, our concentration given to us was in a single unit of volume, 1 milligram per milliliter. Do you remember what the next step would be? Cancel like terms. So let's take any terms that we have that are paired. Let's go ahead and cancel those out. And I'll use a different color here. We have milligrams that matches milligrams, and we have kilograms that will match the 25 kilogram, or the kilograms portion of the 25 kilograms here. We'll use this opportunity to rewrite the question here in just a moment. What do we do with the last term that was left over? We take the last term and we move it to the outside. Okay? We'll move it over here because we know we're going to give some amount of milliliters to the patient. That's the volume that we're going to draw up in the syringe. Let's erase this and move it over. So with this calculation, and after we've canceled our terms, we now have a desired dose of 1 was milligrams per kilogram, but we've canceled milligrams and kilogram, over a concentration of 1 milligram per milliliter. But remember, milligrams canceled with the desired dose here, and we moved milliliters out. 1 over 1 times a weight of 25 kilograms. But the term kilograms was canceled because it was also present in our desired dose. So our math expression that's left is 1 divided by 1, which is 1, multiplied by 25, which is 25 milliliters. 25 milliliters is the volume of medication you're going to draw up and give the patient. The dose that you gave the patient, remember your desired dose was 1 milligram per kilogram, was 1 milligram for every kilogram, and there were 25 kilograms. So your volume administered was 25 milliliters. The dose that you gave was 25 milligrams. That was your dose. I would encourage you to stop here and practice some of these weight-based bolus calculations before you move on to the next one. Most of our patients will express their weight in pounds, so you're going to have to be comfortable with converting pounds to kilograms as part of these calculations. The next type of problem you may see is a non-weight-based infusion. So if you'll note back from our previous formula, the full formula here, we've taken out the kilograms portion from the center because this is a non-weight-based calculation. We're going to have desired dose over concentration times our drops per milliliter. Now, when we look at drops per milliliter, if you're giving an infusion of a medication, which this would be the case, the infusion of a medication, it's safe to assume, unless you're giving fluid or a large amount of volume to a patient over a period of time, that your drip set would be 60 drops per milliliter. So we'll use that as our final term over here. 60 drops, or GTTS, per milliliter. Let's give a hypothetical situation where we need to give a dose of medication at 1 milligram per minute. Our desired dose would be 1 milligram per minute. We'll say that we have a concentration pre-made up in a bag for us of 100 milligrams in 100 milliliters of this imaginary medication. We can disregard weight because there's no weight requirement for this calculation. Our desired dose is 1 milligram per minute of this imaginary 100 milligram and 100 milliliter solution. And we're going to use a 60 drop per milliliter set for administering this medication. All right, let's get into our steps to solve. Our steps to solve this here are first to make sure all of our terms match. And I'll just put some check marks by each of these while we look at them. Our milligrams match our milligrams. Our milliliters match our milliliters. And then we're left with two terms here, drops per minute. When we go to deliver this medication, if we're giving an infusion, we're going to be counting the number of drops per minute that pass through the chamber in giving this medication. So that makes sense for us, and we'll move those aside here in just a moment. So we've made sure that all of our terms match. We don't have something like milligrams in our dose and grams in our concentration, where we would need to convert that grams to milligrams. Everything else seems to be on par. The next step, if you remember, was to solve for a single unit of volume. And so when we solve for a single unit of volume, we're looking at the concentration. And in the concentration, we're going to turn this 100 milligrams and 100 milliliters to 1 milliliter. How do we do that? Well, for this one, we divide both terms by 100. 100 divided by 1 is 1. 1 milligram per 100 divided by 1 milliliter. Well, let's rewrite that a little bit so it's a little bit cleaner. So our second step was to solve for a single unit of volume, and the given concentration that we have is 1 milligram per milliliter now. The next step in the process was to cancel your like terms. So if we look at the terms that we can pair off, and for my math folks, you just have to trust me, the algebra works. You can certainly work this out the long way if you'd like. Let's pair off things that will cancel. Milligrams matches with milligrams will cancel. Milliliters matches with milliliters. Those are going to cancel. Minute only appears once and drops only appears once. So we're going to move those off to the side. Since we know we're giving an infusion and we're going to have to count the drops, we can assume that our calculation should come out in drops per minute. Drops per minute. Now we can rewrite the equation with all of our terms eliminated. And we're left with 1 divided by 1, which is 1, times 60, which equals 60. So we're going to start this infusion at a rate of 60 drops per minute. Our dose is still 1 milligram per minute. That was our ordered dose, 1 milligram every minute. And we're going to drip this in or infuse this in at a rate of 60 drops per minute. Now, a side question from this: how many milliliters would we be giving this patient if we were to run this infusion for a period of 10 minutes? Well, if we're giving 60 drops per minute, and there are 60 drops per milliliter, we can assume that we're giving 1 milliliter every minute. And therefore, if we ran this infusion for a period of 10 minutes, we would be giving 10 milliliters of solution. We also could work backwards to determine, with a concentration of 1 milligram per milliliter, that a total of 10 milligrams of medication would be administered over this 10-minute time period. I encourage you to pause here and practice some of these equations. Let's talk about the last step, which involves all three steps or all three portions of the medication calculation formula. Desired dose over concentration times a weight in kilograms times your drips per milliliter or drops per milliliter. For this problem, you'll start the same way you started all of the others. Take your desired dose, and we'll use an example dose of 1 milligram per kilogram per minute. Sorry for the scratchy writing there with a mouse. We'll take a concentration of 1 milligram per milliliter. We'll say that this patient weighs 25 kilograms. And for the infusion on this one, we're going to use a macro drip set, or we'll say a drip set that is 10 drops per milliliter. Understanding that for most medication infusions, you're going to use a 60 drop set, but I'm going to try and use some round numbers here so that you can get through the math theoretically without being bogged down in the decimals. Our first step is going to be to make sure that our terms match. So when we look at our terms, we've got milligrams matches milligrams, kilograms matches kilograms. We weren't given a weight in pounds. We've got milliliters working with milliliters in the concentration, and we're going to be left with drops per minute. And that makes sense because in infusion, we're going to be counting drops per minute of this solution. So now that we have everything matched, the next thing we're going to do is cancel our like terms. Milligrams here cancels with milligrams here. Kilograms will cancel with kilograms. And milliliters will cancel with milliliters. We're going to be left with two terms, drops and minutes. Those two terms we're going to bring over to the side, and we'll just use drops per minute. And that checks logically for us because, again, we're going to be counting the number of drops per minute. And then let's erase these terms and get them out of our way. We'll make the math portion a little bit easier to deal with. And let's get rid of our kilograms there, our drops here. And so when we get down to mathing this equation, we're left with 1 divided by 1, which is 1, times 25, times 10. And you can see here why we didn't go with a 60 drop set. So 1 times 25 is 25, times 10 is 250 drops per minute. Now we generally like to stay somewhere between 20 and 180 drops per minute, just because it gets really difficult to calculate or count those drops when we get such high numbers, or the variability of medication when we get really low numbers. But we can see that the math theory works here. 250 drops per minute. This skill is going to take some practice, and I would encourage you to work with the infusions and work within the guidelines and protocols that you have at your service and go through and calculate some of those make-believe patients and work through this process.